Welcome back to section 6.1b, where we'll be talking about the different types of solutions and how to read a solubility curve. Recall from the last podcast that a solution is made up of two parts, the solute, which is the substance that gets dissolved, and the solvent, which is the substance that does the dissolving. When two substances dissolve in one another, they are considered soluble, like salt and water. This is probably the most common example used and one that you are most familiar with. It is a solid dissolving into a liquid. But there are other scenarios that can happen. Liquids can dissolve into solids, gases can dissolve into liquids, liquids can dissolve into liquids, and so forth. We will look at some examples in this slide and in the next. If a substance cannot dissolve into another substance, then it is considered insoluble. A good example of this would be sand and water. As mentioned before, there are many types of solutions. We saw the typical solid dissolving into a liquid in the last slide, as well as a liquid dissolving into a solid, mercury dissolving into silver, and a gas dissolving into a liquid, carbon dioxide into water. We can also look at a solid dissolving into a solid. Those would be your alloys: brass, bronze, sterling silver, steel. Brass is a common example. It is made up of copper and tin. Both are solid metals. They are heated up, and then they are dissolved into one another, and they harden back up into brass. We have other alloys like steel, which is a mixture of iron and carbon, and sterling silver, which is a mixture of silver and usually copper. We also have the liquid-liquid scenario, alcohol and water, or acetic acid and water, which is vinegar, and gas dissolving into a gas. Most common example there would be air. Since nitrogen gas is the major component of air, we say that other gases dissolve in it, so oxygen gas would dissolve in nitrogen gas. We do have two other vocabulary terms at the bottom, miscible and immiscible, that describe the ability of a liquid to dissolve into another liquid. This is specific to that scenario only. When two liquids dissolve into one another, like alcohol and water or acetic acid in water, we consider them miscible. And if they cannot dissolve into one another, they are considered immiscible. An example of this would be oil and water. In the first podcast, we talked about the formation of a solution, and we talked about how there needs to be enough solvent, and we use the solvent water, to take away the molecules of a polar molecule or even the ions of an ionic compound away from each other. We talked about how there will be a point where there will be no more water molecules available for the dissolving process. It's at that point that a solution becomes saturated. That means that the solution is full, that no more solid can be dissolved. The visual cue would be seeing a solid sitting at the bottom of a solvent. The other scenario would be an unsaturated solution. These would be solutions where the solute can still fit into the solvent. They are not full, and we can keep on adding solvent to the solvent, and it continually dissolves. The visual clue here is that no solute is visible within the solvent. There is a third type of solution. It is called a supersaturated solution. These solutions have more solute dissolved than a saturated solution has at room temperature. There is no visual cue here. You would need some background information to figure out that you are looking at a supersaturated solution, and we will look at that in a little bit. In this diagram, you can see an example of an unsaturated and saturated solution. In the above picture, 30 grams of table salt is dissolved in 100 milliliters of water. You can see to the right that there is no visible sodium chloride in the solvent water, and so we would say that that solution is unsaturated. However, in the bottom portion of the diagram, 40 grams of sodium chloride is now added to the same 100 milliliters of water, and you can see that there is some salt sitting at the bottom of the container. That is your visual cue that you are looking at a saturated solution. One of the words that we need to talk about right now is solubility. Solubility is the maximum amount of solute that can fit in a certain amount of solvent at a particular temperature. For sodium chloride, that amount is 36 grams. So you can see that there are 4 grams of sodium chloride remaining undissolved. In this next diagram, we have a series of beakers. In the first beaker, we have an unsaturated solution. You will notice the temperature is 25 degrees Celsius, and we are dissolving 95 grams of solute into solvent. Over time, you will see that most of that solute will disappear into the solvent, leaving 9 grams behind. We're still at 25 degrees Celsius. So we will say that we are now at a point of saturation, that the amount of solute that can fit into the solvent has been reached. The maximum amount has been reached. We call this a dynamic equilibrium. Let's break that word down. Dynamic means changing, and equilibrium is when two opposing rates of change are equal to one another. In this case, it is the rate of dissolving and the rate of precipitation. When we look at a beaker that is filled with a saturated solution, with the naked eye, we cannot see anything happening. But at the nano level, we would see that particles are continually dissolving into the solvent, and because the solvent is full, solute particles are being squeezed out and brought back down as a precipitate to the bottom of the beaker. So there are continual changes of the solute dissolving into the solvent, and then the solute particles coming back out and precipitating at the bottom. Now, when we apply some heat, you will find that the temperature increases to 50 degrees Celsius, and all of that extra solute sitting at the bottom has now disappeared. We are at a state of unsaturated again, but we are at a higher temperature. One of the things that we have noticed is that when we increase the temperature of a solvent, we increase the solubility of the solute into the solvent. More solute can dissolve into the solvent at a higher temperature, but this is a temporary process. If I was to cool back down the solvent to 25 degrees Celsius, I would revert back from an unsaturated solution to a saturated solution. There is a third scenario, and that is called a supersaturated solution. That is the picture of the beaker in the far right corner. You can see that all of the solute has dissolved in the solvent, and we are back at room temperature, 25 degrees Celsius, and there is no precipitate at the bottom. Notice that earlier on, we did see precipitate at the bottom. So this is a special situation where we take a saturated solution, we increase the temperature, all of the extra solute disappears into the solvent, and if we can cool it back down to room temperature and that extra solute stays within the solvent, like you see in this bottom right picture, it is considered a supersaturated solution. It's very unstable, and just the slightest disruption of the forces within the solute and the solvent can cause it to go back to saturated state very quickly. And that's what you see in this last picture. So here's a picture of a supersaturated solution. It looks clear like an unsaturated solution, so you would have to have some background information to determine that this was a supersaturated solution. I'm telling you, it's above and beyond extra full of solute. And the only way that you would be able to determine that is by seeding it. And that's what you see in this upper corner right here. It is a few particles of the solute that has dissolved into the solvent. Notice that crystallization begins here and continues. You can now see that this beaker is showing a saturated solution. All the extra solute that was stuffed within the solvent of that supersaturated solution has come out. When looking at this picture, you would think that it looks very cold. It looks like ice, but it was actually a very exothermic process. There is tremendous amount of heat energy being released as the new attractive forces between the solute and the solvent come back together. So as mentioned in the previous slide, the higher the temperature of a solution, the more solid can be dissolved within the solvent. That is not the case for when we're trying to dissolve a gas into a liquid. The higher the temperature of a solution, the less gas can actually dissolve. And you can see that in this bottom picture. At higher temperature, we have less ozone being dissolved, 1, 2, 3, 4, 5, 6 molecules, versus probably 12 to 15 molecules being dissolved at the lower temperature. If we look at the graph on the right-hand side, you will see that as the temperature increases, the solubility of the gas will decrease. Carbon dioxide at 10 degrees Celsius is somewhere about 2.25 grams per 100 grams of water. And if we increase the temperature to about 60 degrees Celsius, you can see that now a little less than 1 gram of CO2 gas can dissolve per 100 grams of water. On the graph to the left, you can see the solubility of a solid being affected by temperature. And we had mentioned earlier on that if we increase the temperature for most solids, you will see an increase in solubility. Let's take, for example, potassium nitrate. You will see that at 0 degrees Celsius, it's probably about 15 grams can dissolve in 100 grams of water. And if we raise the temperature to 60 degrees Celsius, we can now get close to 120 grams of KNO3 to dissolve in 100 grams of water. Do notice that sodium sulfate does not follow the typical pattern. Once again, most solids will increase their solubility as you increase the temperature of the solvent. There is another variable that can affect the solubility of a gas in a liquid, and that is pressure. Henry's law says as the pressure above a liquid increases, the solubility of a gas within a liquid will also increase. Notice in the diagram that if we increase the pressure, more gas molecules are forced within the solvent, as seen in the figure on the right. One thing to remember is that pressure does not affect the solubility of a solid within a liquid. It only affects the solubility of a gas within a liquid. The last thing we need to look at is how to read a solubility curve. You will notice that the graph is very crowded, so we need to be very careful in identifying the particular solute that a question is referring to. The other thing that you need to look at in a solubility curve is that temperature will always be on the x-axis and solubility will always be on the y-axis. Now, one of the most important things to remember about the solubility is that these numbers right here reference the amount of solute that will dissolve in 100 grams of water. When you are reading a curve, you want to find a data point on the graph, and that will usually be the intersection between the temperature and the solubility of the solute in the solvent. If that data point is below the line of your solute, it will be considered unsaturated. So, for example, I want to dissolve 20 grams of NaBr into 100 grams of water at 20 degrees Celsius. So if I come over here to 20 degrees Celsius and I jump up to 20 grams, which is about right here, if I find my sodium bromide line, which is right here, you will see that that red dot, that data point, is far below the blue line. And so we would say that it is unsaturated. Now at that same temperature, I'm going to try to dissolve 160 grams of sodium bromide into 100 grams of water. So now my data mark is going to be about right here. And you can see now it is well above the line. So we would say that this would result in a saturated solution, and that there would probably be about 43, 44 grams or so of the sodium bromide sitting at the bottom, because this point right here is the maximum amount that can dissolve at that particular temperature. That is saturation point, which to me looks like about 118 grams. So if I'm trying to put in 160, the difference between those will be the 100 and, well, actually not 100, but about 42 grams or so. Let's look at one more example. Let's say we're at 0 degrees Celsius and we're focusing in on dissolving sugar in water. If we go up to this line right here, you will see that the maximum amount of sugar that can dissolve in 100 grams of water is approximately 180 grams. We would say that this marks saturation. This is the maximum amount that can dissolve. So if at 0 degrees Celsius, I try to dissolve 120 grams of sugar into 100 grams of water, it will dissolve because it is under the line and it is considered unsaturated. However, if I try to dissolve 200 grams of sugar into the 100 grams of water, about 20 grams will remain on the bottom, undissolved, which tells me that I have reached saturation point. The extra solute cannot fit into the solvent, and thus it sits at the bottom. Now, one last thing, not to confuse you, but if the question was phrased such as, I was able to dissolve 200 grams of sugar into 100 grams of water, then we would say that it is a super saturated solution because we know that it happened and we knew that 180 grams was the maximum amount, and because of special circumstances we were able to get that extra 20 grams or so into the solvent. So be careful with supersaturation. It doesn't happen all the time. You got to really watch the language of the questions given to you. All right, so let's take a look at a couple of examples. The first question says, what kind of solution occurs when 40 grams of potassium chloride is dissolved in 100 grams of water at 60 degrees Celsius? The first thing we're going to do is go to 60 degrees Celsius, which is right here, and we are going to go to the 40 gram mark, which is right here. We are then going to look for the KCl line, which is right here. And you can see that the little blue dot is just below the red line, which means that this is a unsaturated solution. In the next question, it says, what kind of solution occurs when 40 grams of KCl is dissolved in 100 grams of water at 40 degrees Celsius? So once again, we'll go over to the 40 degrees Celsius line, and we'll move up to the 40 degree mark. And this time, you can see that that red dot is exactly on the red line. So now we are looking at a saturated solution. You will also notice that as the temperature decreased from 60 degrees Celsius to 40 degrees Celsius, less potassium chloride can dissolve. The third question says, what is the maximum amount of sodium bromide that can be dissolved in 100 grams of water at 60 degrees Celsius? So this time, there is no data point. We need to figure out what that data point is. So we're going to go over to 60 degrees Celsius, and we're going to go up until we get to the sodium bromide line, which is right here. And you can see that 120 grams is the maximum amount that can dissolve in 100 grams of water. Question 4 says, what is the maximum amount of potassium nitrate that can be dissolved in 100 grams of water at 70 degrees Celsius? So we're going to do the same thing we did in the last question. We are going to go to 70 degrees Celsius, and we are going to move up until we hit the potassium nitrate line, which is about right there, and that is 140 grams. According to the diamond mark in question 5, how much of the KNO3 has been added to the water at 70 degrees Celsius? And we can clearly see that that is 160 grams. So we've added 160 grams. We know the maximum amount is 140 grams. So question 6 is asking us how much extra potassium nitrate is sitting at the bottom of the container at this 70 degree temperature. And hopefully we remember that we subtract those two values together and we get about 20 grams of the KNO3 remaining at the bottom. The last thing we need to talk about are the 3 factors that affect the rate of hydration. The first one is temperature. We, of course, know by now that temperature is a measure of the average kinetic energy. So if we increase temperature, we're increasing the motions of the molecules. Solute and solvent particles will come in contact with each other at a faster rate. Particle size, that deals with surface area. If we take a cube of sugar and we pulverize it into many granules, smaller granules of sugar, there will be more particles coming in contact, solute particles coming in contact with solvent, which would also increase the rate of hydration. And then, of course, agitation or stirring. If we were to naturally let the solute and the solvent intermix, it would take a lot longer than if we were to actually purposely move the solute and the solvent towards one another through the process of stirring, thus increasing the rate of hydration. Don't get these factors confused with the factors that increase the solubility of a solid or a gas in a solvent. I want to just remind you as well that the first two factors, both temperature and particle size, are also factors that increase the rate of a chemical reaction, which we discussed earlier in the year. This concludes our second section of 6.1. Please make sure to practice with your solubility curve diagrams and understand the difference between an unsaturated, saturated, and supersaturated solution.